Howdy, everybody. Hope you're doing well whenever you are. We are here for part 3 of Z3 with Rust. Hopefully you've been enjoying the course. I'm always welcome to feedback, so if you have any ideas for improving it, let me know, especially if you find bugs or things in the code. Happy to make changes to make things look well. Today we are going to talk about the optimizer, right? So last time we talked about the solver, the idea being, can you find a solution to a problem? Whereas with the optimizer, we're asking ourselves, can we find the best solution? So hopefully that'll give you some ideas of maybe what we're going to be going over. So I'm going to be working here in part 3 in this folder, and we'll be doing some stuff in there. But before we do that, let's get on to our homework. So I gave you some homework last time on the magic square. If you remember, that's kind of a, I mean, it can be any size, but generally speaking, you have like maybe a 3x3 grid like this. And the idea is you're trying to find values that sum to 15 in every diagonal row and column. So maybe if you put 5 here and 7 here, 5 plus 7 is 12, we'd have to put 3 right here, right? In order to get 3 to be high enough, maybe you put a 6 right here now to get you to 9. Got to do that, and then you can't do that because you'd have to put a 7 right here, right? We've already used the 7. So that's the idea. That was the homework: is can you build a solver that will figure out a solution to a magic square? I gave you a couple extra credits too. So one of them was, can you find all of the solutions, right? So not just a solution. Can you find all of the possible solutions? And then the other one is, could you write it to work on an n by n grid? So I'll show you all the solutions. I didn't do the n by n grid part, but presumably you could think of adding variables here. Obviously it does change the total from 15 to something else, but hopefully you'll see how this solution works. And I'd love to see yours. If you did something maybe better or easier than mine, I'd love to see how you did it, how you solved it. So please send me your code. Again, you're welcome to fork it and send pull requests or changes, or just let me know. I'll check it out. Here's my solution. I start with a solver, and then I'm going to create a 3x3 grid of variables. So that's these right here. And we're just going to basically use that as like the values. Okay. So we're going to keep track of each position. Excuse me. And then we're going to keep track of all of the cells. And the reason why we do that is we're going to assert that they need to be distinct. Remember, in the example we were talking about, I can't use, if I've used the 7 here, I can't use the 7 here as well, right? That won't. Yeah. So what do I do? For each of the cells, I say they have to be greater than or equal to 1 and less than or equal to 9. That is, we're doing an inclusive range of 1 to 9. And then, excuse me, we're going to assert that all of those cells need to be distinct. So we've created the cells. Notice I'm using the grid, right? And I'm using the cells in here, but we're tracking all of the cells in the value. I hope that makes sense. You could potentially have done this in a single operation, but just to kind of highlight that we need to do these steps, right? Create a grid, and then we need to assert the values and then set that they're distinct. I kind of did it separately. But this is the distinct function that I had mentioned you might have to use. And essentially what you do is you give it a list and you say a list of variables, and you say these variables must be distinct. So the next step then is to sum all the rows and the columns and the diagonal, right? Those are like the other constraints of the problem. We've dealt with the constraints of they all need to be distinct. Now we need to say all the rows have to equal 15. All of the columns have to equal 15. And then each of the diagonals have to equal 15. Notice in all these cases, I'm using that grid, that original 3x3 grid that I built, right? So these are the variables. And this is what's allowing the solver, I guess, the solver part of it, to say these are all the same variable. And with those variables, the ones that are in the rows need to sum to the correct to the same value. The ones that are in the columns need to sum to the correct value. And then the diagonal ones need to sum to the correct value. Then all I just have to do is go through the solver and I can print each of them out, right? So I can say, after it's found a solution, print all of them out. And in my case, I'm going to return all of the solutions. So I say, I tell the solver, hey, give me all the solutions, and I want to get the grid back. So it's going to return the grid, and I can iterate over the grid and out. So here's what the solution looks like. If I run it, I can do magic square, this right. And you can see it found a bunch of solutions, right? Notice all of them have 5 in the middle. That's interesting. Essentially, the way the magic square works is the middle value in the number has to be in the middle, and then you kind of rotate around it. You can read more about magic squares, but then you can like rotate any of the values. So 1, 9 is here, then reversed, then up here. No, different variations of like where do you put 1 and 9, and then where do you put the other value. 1 and 9 are also an interesting one because they kind of delineate how the rest of the values go. Obviously, if there was like an n by n, so you're solving a 4 by 4 or 5 by 5 or whatever, you definitely then have like different middle parts to it. You might be able to rotate those differently or solve them. Before we move on though, I do kind of want to show you what's happening underneath the hood. So I can actually do a print line of the solver like this and run this again, and it will actually show you all of the assertions, right? So, or if you've seen Lisp before, it kind of looks a lot like Lisp, right? But I can show you all of the things, right? So I've declared 9 variables. These are each of my cells. And remember how I'd mentioned before, we're like reusing those cells all over the place? Well, here's all of our assertions. And so we're saying x0 has to be greater than or equal to 1 and less than or equal to 9, right? And then we do that for each of the things. Under the hood, you're actually, when we're doing this stuff in Rust, we're building this kind of like meta language that we pass to the solver. Again, there's like some details under the hood that maybe simplify that or make it easier, but like you could potentially take this and pass this to a generic Z3 solver and it would build it, right? But it's just something to look at, and I think it's a good way for you to like see the different values and variables and how they're being created. So we've created 9 variables. For each of them, we've said they have to be within the range inclusive bounds 1 to 9. And then we assert that all of the values have to be distinct. I just counted to make sure that was right. Yep. So we've said all of them have to be distinct. And then we say these ones, all of these, the rows have to sum to 15. The columns have to sum to 15. And then the diagonal have to sum to 15, right? So these are all of our assertions that we've done. We've used Rust code, right? So we've created variables up here, and we've added constraints here, 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 and here, and that's turned into this thing right here. And this is a compatible way to like share these things, right? So if your friend is doing it in Python, you could potentially send this to them, and there are ways for you to import, you know, the this format, this more Lisp style, and in different languages, including Rust. Okay. I just want to show you that because you can see it creates a tree-like structure for some of these things right here. So that's something we'll talk about in previous things, or in future things. But I just wanted to show you that. Again, this is just, we're solving the magic square. We were able to do it with not a lot of code, right? Again, I think this is just like any programming problem. You're asked to do something, you immediately ask yourself like, well, what are the constraints of that I need, under which I need to solve the problem? And so, you define some variables, add those constraints, and then call the solver, right? In this case, it's for a magic square. So there you go. I'd like to talk about the optimizer today, like I said, and I've got a lot of the code here. I think the biggest thing to keep in mind is that like what's changed between just a solver and an optimizer is that there's this notion of minimizing or maximizing. So you're no longer just interested in is there a solution? You're now interested in is there a best solution? That's all that's changed. And the way we do that is we call minimize or maximize on our optimizer. Okay, so we would normally call, the solver dot solve, but now we're going to be calling minimize or maximize, and that's really all that's changed. You still define variables, you still make constraints, but now you just tell it, hey, what is the best solution? And I'd like to start out by describing one way to use this through the knapsack problem. So if you've heard of this problem, if you haven't heard of this problem before, it's a pretty common problem that you try and solve in computer science. I imagine most people who've been to like traditional school may have seen this problem before, or you've probably seen videos about it before, things like that. The way the problem works is you're given a knapsack, a backpack, and it can hold a maximum weight. And your job is to try and maximize the amount of money you can get given a weight limit. So you can see some of the books, all of the books have a price as well as a weight. And your job is to pick among these prices the ones that will get you the most without going over 15 kilograms. So the reason why this is slightly more complicated than just pick the biggest, right, is because we now have different ratios, right? This one will net you $4, but it costs 12 kilograms, while this one will net you $10 at only 4 kilograms. So you can kind of infer that you probably want this one in the bag, right? But now you've got 11 more kilograms to work with. You can't put this one in either, right? So there are some like limitations on picking the right one. I think traditionally you would have learned to solve this with something like dynamic programming, right? Where you'd like pick one and then find the best, and pick one and find the best, and kind of recursively do that, doing some memorization. Right? There's definitely other ways to solve it though, just to be clear. So how do we solve this with Z3? Well, it's probably already going through your mind. Obviously, I have some weight limit that I can't exceed. And then I have these different values and variables, right? So I'm going to have some, I don't know, some variables for each of the items. So we'll say I0 costs or nets me 12, what was it? $4? $4 at a cost of 12 kilograms. And I1 maybe nets me $10 at a cost of 4 kilograms, and so on and so forth. So we probably need to track these things, right? We need to track each of these, and then we need to say, the tricky part here is we need to say if we pick this item, that is allocated towards our 15 kilogram limit, right? So we probably need some kind of constraint on this 15 kilogram. And notice how I said if I pick this item, I need to include that in my weight limit. Okay, that's where we're going. We're going to introduce a new tool called if then else. And the way if then else works is with the optimizer. You can say if then else for some Boolean value. You can say for some Boolean value. You can say if then else, and then you give it a true condition or a false condition. So what this allows the optimizer to do is to say, if I set this to true, here are the consequences, right? So these are the consequences of changing this value, right? So in our case, we can say, well, the consequences of setting this value to true is that we net $4, right? But we expend 12 kilograms. Same thing for here, right? Well, if this one is true, we net $10 at the cost of 4 kilograms, right? And so we can do that. We can do that if we use these as booleans and kind of say if then else, right? If it's true, then we net $10, but we cost 4. And then we can go through our thing and say, hey, we need to set a limit on how many of these can be true. You can never go over 12 kilo. You can never go over 15 kilograms. So you could see if we only had these two, we couldn't pick them both, right? Because we'd go over the limit. So we'd have to pick one. In this case, so if we're saying we want to maximize, the thing we want to maximize on is right here, right? We want to max this value. And we want to limit this value, right? Hopefully that makes sense. Let's go look at code. I think it'll make more sense when we look at it. Here we go. Okay, so I have my values. I've entered them in, or my items. I've entered them in here. So we have one that with a value of 4 and a weight of 12, value and weight of 2, value of 2, weight of 1, all of the different values, right? And we've set our limit to 15. We're going to create a bunch of Booleans for each of the items, right? And so we're going to say these are the ones that are like taken or chosen. So it's a Boolean value. If we choose it, it's true. If we don't choose it, it's false. That's what we're going to allow the solver to pick from. Now we're going to build our expressions for the total weight and the total value, right? So these are integer values, but we're going to go through each of the items and pull that Boolean value out, right? And we're going to say, if it's taken, the weight of this item is an if then else. It's the item weight if it's true, or it's 0 if it's false. And the value of it is the item value if it's true, or 0 if it's false. So this is just a fancy way of creating an if condition. where we say, based on the item taken, if it's true, we need to include that weight. So you see we add the weight right here, and we need to include that value, the value right here, in our total weights and value, right? Um, Hopefully that makes sense what we're doing. We're just going to go through all the items and create these if then else's. Say, hey, if you use this, it's going to cost you this much, but you're going to get this much. If you don't, it's not going to cost anything. It's not going to affect anything. Okay. So we're going to do that for each item. And then, so that's building up our constraint list, right? And then we can say, now we can say, hey, the total limit or the total weight has to be less than or equal to our limit, which is 15. And we want to maximize on total value, right? So just like what we talked about here, we want to maximize the amount of money we make, but we want to limit the weight to no more than 15. And then we just tell it, hey, solve the problem. So for an optimizer, there's usually only one solution. So we just check to see if there's a solution, and then we can get the model. I do want to print it out so we can do the solution. So let's do that really quick. Oh, what I called it. And then let's run it. And let's see what we get out. So you can see here, it's created, again, we've created our little Lisp style code where we're going to create 5 Boolean variables. And we're going to make an assertion, right? So we're going to assert that if we pick A, it's going to cost us 12. If we pick B, it's going to cost us 2. If we pick C, it's going to cost us 1. Pick D, it's going to cost us 1. It's going to cost us 4. And we want to assert that that's less than or equal to 15, right? So this is our weight limit. We're saying if we pick those, if we set those to true, our weight limits have to be less than 15. And now we're telling it to maximize the value we get from doing it, right? So if we pick E, we get 10. If we pick D, we get 1. If we pick C, we get 2, and so on. So, and what does it do? It spits out a solution for us, right? It says, here are the things that you should put in your backpack. It'll get you $15, and it will cost you 8 in weight. So we definitely have a gap. But if you think about it, we've picked all of the items but this one. All of them but A. The reason being it's absurdly expensive for very little value. So the optimizer has done that job of like picking the right thing, okay? So I just want to review this really quick. Again, one time, we're using Boolean values here because we want to toggle whether or not we've used an item. And then based on whether or not we've used that item, we want to increment our weights or our values. And we add that to our total weights. I hope you can see that the code is very Rust-like, right? Even though we like end up with something like this from the solver, this looks very Rust-like, right? We're creating variables, we're doing for loops, we're assigning those values to for loops, and then we just tell the solver, hey, here's how I want you to solve it. So I think they've done a really good job. Previous versions were a little bit harder to use, and they've definitely gotten better. And I can see it continuing to get better in the future. So very, very cool way to solve. Okay, we can use this to answer very crazy questions too, right? Optimization questions. Last time we did an advent of code problem where we were trying to hit hailstones with a single rock. This time we're going to do this year's advent of code day 10, part 2. So you can actually go back and see how I solved it. There is a linear algebra way to solve this, but the power of the solver is, I think I'll show you, we could just loop through all the machines and for that day, and there's not a lot of code to like find the minimum function, right? I've made this a little verbose so that you can kind of step through it and see what's happening. You could easily get this down to like 10 lines of code, whereas before my original solution was like, I mean, I had to do dynamic programming plus Gaussian elimination. And so it was a lot of code, right? Let's talk about the problem though before we get too far into it. The way the problem works is you have a set of buttons, right? Maybe we should try and follow the pattern here for this first. We have 6 buttons. 1, 6. So we have 6 buttons, and they're all connected to some lights. 4 lights. And their connections look a little bit like this. This one is connected to this one. This one connected to this one. This one. This one to this one. This one. This one. Did I miscount those? 1, 3, 1, 3, 2, 3. Okay, we'll try one more time. No. There's 4 buttons. Let's try it again. 3. So this one goes here. This. And then this one goes 1. Yeah. 3. 2, 2, 3. 2, 3. 0, 2, 0. That's an ugly diagram. Should I do them different colors? Maybe it'll make more sense. So this one goes to 3. This one goes to 1, 3. This one 2. Goes 3. Okay. I think that makes a little bit more sense. That's a little bit more to understand. But the idea is every time you press a button, it increments. So if you press this button 1 time, it's going to increment this one. If you press this button twice, let's say, match colors. If we press this button twice, it's going to increment this one twice and this one twice. So this one now has a total of 3 intensities, right? It's in right? And so then if we, let's say we press this one, it's now going to, increment this one and this one, right? Hopefully that makes sense. So they have a target set of values that they want you to meet, right? So they say for this one, 3, 5, 4, and 7. So they want this one to be 3, one to be 5, 4, and 7. And the question they're asking is, can you minimize button presses? Okay, they're asking you, can you minimize the button presses? So there's various ways that you could solve this. Some of them obviously would take a lot of button presses, right? So you could imagine like if you used just this one, increment this one, You probably actually couldn't ever use this button much. The reason being is like this line right here affects these two, right? So you may say to yourself, oh, in this case, I probably want to press these two. I probably want to press like this button, say 4 times, because that will get me 1, 2, 3, 4, and then 1, 2, 3, 4 here, and then is that right? Yeah, get me 4 there, and then I can press this button 3 times to get the rest of those. 2, 3. So now I've met these two. So then the question is like, how many of these buttons do I press? Well, now I'm in trouble because if I press this button 3 times, right? So I press this button 3 times, I get 1, 3, and then 3. But now there's no way for me to get 5 here, right? Because if I press this one once, this one is now exceeded, right? So you can see it gets very complicated. You have to start like picking the right values to do this. Like I said, there is kind of like a linear algebra way to do this, where you're like, you do button presses like this. And then the solution is like, 3, 5, and 4. You can solve this and then figure out what's missing, stuff like that, right? But it's very complicated and it takes a lot of work. And maybe you've never done linear algebra. You can solve this though with Z3, right? If you spend a second thinking about it, this is definitely solvable in Z3, right? Remember, we want to define our variables, and then we want to express our constraints, and then we want to tell it to optimize on something, right? Well, we can get the optimize pretty quickly, right? The optimization part is we want to minimize the button presses. So this is our optimize, right? So now we just need to figure out like what our variables. Well, we probably need a variable for our button presses, right? So add those. We probably want a variable for our intensities, right? What do I call them? Targets. Our target. So we probably want to have some variables for this, right? Now our constraints, maybe we need to think about a little bit. How would we solve our constraints in this case? Well, one way to think about it is whenever we push a button, we need to increment a value. So maybe the way to describe it then is our constraint is we want to meet the target value. And pressing a button affects those values, right? So whenever we press this button right here, we want to say that has an effect on this value right here. I think that's maybe the best way to think about it is when we press a button, we have the number of button presses in our buttons, and then we have our targets, and we want to create a relationship between a button press and a target, right? So this one here actually has 2 relationships, right? It's related to this one and this one. So we need to say whenever you press this one, you need to increment this value as well as this value, okay? Let's go look at it in code now. I think we've gotten enough through the problem that it'll make more sense. So we're going to create our machines. We have several of them, right? So I have several example machines that we can go through and look at. We're going to track the total presses of all machines, okay? Because that's how we're going to like solve the problem at the end. we go through and sum up all the presses of all the buttons, and then we're going to loop through each of the machines and create a new optimizer. And then you can look at the end, we're going to solve each of them on their own and increment that total value, right? So we solve each one on their own and then increment that value. But otherwise, inside the for loop, it's the same as what we've done before, right? We're going to define some variables. We're going to say, hey, I want to push each button, or I'm going to create a button for each of them, right? The number of presses for each button. Obviously, we have to have it greater than or equal to 0. Again, if you're familiar with linear algebra, one of these may become like -1. Obviously, we can't push a button -1 times, right? So, oops. Can't push a button -1 times. So we say, hey, assert that each of them have to be greater than. Then we can go through each of the targets and create a sum for that target. And we just loop through all of our buttons up here, all of our little buttons. And we say, hey, if it's affected by that button, that then the sum of this target is the sum of that target plus this button, right? We want to add this button to our sum for this current target. And then we just assert that that sum needs to be equal to the value. Okay. I hope that makes sense. So we're going through each of these values. Maybe the steps to think about it is we go through each of these values, and we say which buttons affect it. So in this case, it's these two right here. And so we say, if you press this button or this button, it increments this sum. So we would say like the sum of of target 0. So the sum of say the sum of target 0 is equal to button 4 plus. Okay, that's essentially what we're doing. Hopefully that makes. We're going through there, and so we just have to loop through all the buttons, find the ones that are affect this one, and then add that to our sum. Again, this looks very much like Rust code, but this is a variable in the solver that we're creating sums against and then setting a constraint on it. It has to be equal to our target value. Okay. Now we want to minimize the total presses. So we create a sum of the presses as a variable, right? So we say for each of the button presses, we add that to our sum presses, and then we want to minimize the sum presses. That's what we do right here. This is our solve the problem, right? Minimize this value. Then we can go to the solver and check it. And in this case, it's a puzzle, so it's meant to be solvable. So you get the model out, you get the sum of the presses as the minimum number of presses because we asked it to minimize it, and that will give us the value, and then we can sum those all up to get our. So let's just run this to look at it. You can see here we have 3 machines. Here's the minimum presses for each of the machines, and then sum together that equals. I hope this has helped make sense. Is like we had a very complicated problem, but if we kind of step through it, if we kind of think about it, we can recognize what is it we're trying to optimize, right? What is it we're trying to optimize? And then what are the variables and constraints that we need to give Z3 to do that optimization, right? So we were able to do that by, again, making buttons, making target sums based on how many times those buttons were pressed. And then we were able to sum all the presses and say, I want you to minimize on that thing. We can do this one more time just to see it, right? So we can, after we've done all this, I think the reason why I keep showing you this is because if you ever, I've noticed, like if I ever have problems, like if I've written it out in my mind, or maybe even on a diagram or whatever, I've kind of written out what I wanted. and it doesn't end up working the way I expect it, doing this is helpful because I can now read what the solver thinks I've done. Well, we can read what I've told the solver and see if it's what I think it should be. Maybe is the better way to say it, right? So you can see here I've said, okay, for this specific, and let's look at the machine for this specific machine, right? I'm interested in, I have these buttons, and they all have to be greater than or equal to 0. These are the button presses. And then I have these summations. So do you see here this first one where we say button 4 and button 5, its presses added together need to be equal to 3. I want you to assert that the sum of these buttons is equal to 3. And then I do that, so on and so forth. And then I say, now I want you to minimize on these key values, right? Which are the button presses up here. Okay. We've defined variables. We've set constraints on those variables, and then we tell it minimize on those things. Check sat is just, obviously you have to check if it's solvable before you can. And there you go. You've taken a very hard problem that requires linear algebra. You've been able to solve it without any linear algebra, right? You can just reason about it with the solver and come to a solution with it. So there's a lot of power in the Z3 solver. I hope you get that by looking at this. Again, I've made this code a little verbose for your own viewing, so you can kind of read and see what's going on, and maybe make it clearer than I would for a normal puzzle solve. But it's actually not a lot of code compared to how you might solve it with linear. So again, a very powerful tool for solving puzzles, but also solving things in real life, right? There's lots of times where you have a problem and you want to optimize a solution to something. Being able to throw it into a solver like this can give you some, like, that's what I think is cool, is like there's a lot of times at work where I've wanted to do something like this and just had to reason about it and hope my reasoning was correct. Now we can put it in the solver and actually validate that reasoning. So I kind of want to give you, for this next example, a similar style thing. It's a toy answer, I'll admit. It's a bit of a toy answer, or a toy problem, but I think it will help us learn about soft constraints. So what we've done in the past is we've said we want to assert that some value equals this, or some variable equals this value, or the sum of these variables have to be less than or equal to this value, something like that, right? Another thing we can do with the solver, though, is with the optimizer. It's technically, I mean, you'll see you'll see, but I put it in here because we're trying to solve problems, but we have soft constraints. So we want to allow for some variability, and then have the solver pick the best based on that. And the way you do this with soft constraints is, instead of asserting something, you say, I want you to assert this softly, and then you give it the expression that you want to assert softly, and then you give it a weight. And the way I want you to think about the weights is the solver will want to maximize the weights within the same group. And so maybe we can just do this with a quick example. Let's say we have an equation like x plus y plus z, that's equals 50, whatever, right? And we say x has to be greater than or equal to 10, y has to be greater than or equal to 10, and z has to be greater than 10. So we'll call these asserts, right? These have to, we say these have to be the case, and then we can tell it to solve the problem here, right? And maybe it will say, oh, well, we could do 20, 20, 10. That would be a valid solution. Perhaps, though, we want to give it a soft constraint, right? Where we say, hey, for this value of C, of Z, we say if Z is less than 10, less than 15, maybe, I'll give you 10 points for doing it. If Z is greater than or equal to 30, I'll give you 80 points. And if Z is equal to 25, I'll give you 100. Okay. And we make these soft asserts, right? We say, well, I don't know exactly what Z is. You can figure out what Z is, but if you can get Z to be 15, I'll give you 10 points. If you can get it to be 30, I'll give you this. If you can get it to be equal to this, I'll give you this. Let's add another one. We'll say if Z is equal to 100, I'll give you 1,000,000. Okay. We're just going to add one here as an example. So what the solver is going to do is it's going to kind of figure out what values it can set for X, Y, and Z, but it's going to try to set Z based on these soft constraints. And it's going to try and pick one to maximize these things, right? So obviously the first one it's going to try and pick is this Z equals 100, right? So it'll say, hey, can Z be 100 because I'll get 1,000,000 points for it, right? I want to maximize that. So I want that to be 1,000,000 points. Obviously, we can't do that here because Z would be 100. We could never get the value to 50, right? So it's like, oh, I can't do that one. I'm going to ignore it. We can go through the list. This one definitely works, right? We could set it to 10. That would work. We could set this to 30 and then these two to 10. That would definitely work. We could also set it to 25, exactly 25, and then just have these cover the rest of the 25, right? Make one 10 and one 15. That would totally work. So these three are definitely feasible solutions. Now the assertion model is going to pick the one that's the best, right? And so it says, oh, this one's 100 points. So I'm going to pick a value that is this. So now when you've told it to solve, it's going to prefer to set Z to 25. And then these can be anything else, right? This one's 10 and this one 50, right? But it's going to pick this one right here because of these assertions that we made for the thing. You can imagine this working in like many ways, right? Imagine a computer where you're trying to pick between, you have a new computer you want, you're trying to pick between 10 or 15 of them. And so you enter in some specs and you say, I definitely have to have, NVIDIA 3060 or greater. And I definitely have to have, 16 gigs of RAM. And I definitely have to have, an AMD 7600 or whatever. 3D. So those are like my limits. I have to have those. But you say, if you can get me 32 gigs of RAM, I'll give you 50 points for that. If you can give me 64, I'll give you 80 points, right? But you have to stay within the price cap of the thing. And so what the solver will do is, and maybe you do that for other things too, right? You say, for the hard disk, if you can get me 2 gigs, I'll give you more points for that. And if you get 4 gigs, I'll give you even more points. And then you can choose priorities, right? So maybe you would say 16 gigs is worth 20 points and 32 gigs is worth 40. And then 2 terabytes is worth 80. And then 4 terabytes is worth 90, right? Now it will go try and solve the problem, but it will try and pick ones that are going to maximize these values, right? So it's going to prefer to find computers that fit these criteria, right? And maybe it can't find one that fits both of those, but maybe it can find one that fits these two, right? And so now it's like made some kind of model that's better. That gives you 120 points. It's going to prefer to do that. So again, this is a way of saying maybe I don't have there's not a limitation, but I have preferences. Maybe that's another way to say it. I have preferences, and I'm going to assign weights to those preferences, and I want you to maximize those preferences. So we're going to create, and we're going to do one with time constraint, right? So imagine scheduling a meeting. We want to schedule a meeting and pick a time, and we want to assign weights to those times based on the person, right? Excuse me. So I'm going to walk through a couple examples here that this is on the repo, so you can look at it. Assume that you have Alice and Bob. Alice wants it at 9 a.m. and Bob wants it at 10, and they both get a score of 10. They're at the same like level, right? In this case, the system can pick arbitrarily what you want to do, right? Because both of them have an equal score, it will just pick one, right? But let's say it's between now Alice and the boss, right? Well, it's definitely going to pick the boss's time because his score is much higher. So there's this unequal weight, right? So it's going to prefer to satisfy the boss because it's going to net 50 points, whereas Alice only gets 10. We can do this substantially more complicated, right? Let's say you have Alice and Bob each with 10. You have Charlie, who is like an executive, and he's worth 55 points. And then you have the boss, who's worth 50, right? So we add Charlie, who's an executive, he's worth 55, and he wants it at 11 a.m. Well, you might say, oh, we should definitely try this one. It nets us 55 points. But if you look, both Bob and the boss want it at 10, and theirs is worth 60, right? So in this case, you'd end up picking the bosses and Bob's because the total net is 60. And that's essentially all there is to this thing, right? So how do we do that in code? Well, we create an optimizer. We make any of our hard constraints. In this case, we say the meeting has to be between 9 and 11. And then we just add our preferences. And notice we say, instead of asserting, we assert soft. So we say for each of our preferences, assert soft, and we assert the preferred time and the preferred weight with some level of preference, right? Or this is the group, I should say, and this is the group of preference, okay? This is what groups them together. This is something that you kind of have to keep in mind when you're doing this. Grouping them together gives them like the same values. So if you have different things that you want to assign different weights to and have it pick those things, you want to like, for example, you want the RAM in one group, you want the memory in the other, okay? In this case, because the preferences are all one variable, you just have one set of soft constraints. But we're saying, here's the times, here's the preferred weights. It has to be between 9 and 11, right? You could imagine I could add someone that wants it at noon. It would just discard their preferences because they know it's not possible. But once we've added those preferences, Z3 will just automatically maximize to satisfy those weight or like minimize the violation. I've decided to stick with maximizing, but if you read a lot of the documentation, it talks about minimizing the penalty. It's like two sides of a coin, right? To some degree. But we basically just say, hey, can you find the most satisfiable thing among these preferences? And it'll pick it. Okay. So you can see here, I've printed out all those, or I've created scenarios for each of those three things we've talked about. And if I run it, you can see here's the different constraints, right? So in the first scenario, it picks 10. In the second scenario, it picks 10. This one was arbitrary, if you remember. This one, it picked it because the boss has a higher weight. And this one, it picks it because the sum of the two weights is the greatest, right? You have Bob and the boss at 10. So it picks 10 instead of picking Charlie. Hopefully that makes sense. I think this is a powerful like tool to say, oh, I have some very hard constraints, but I have soft constraints that I prefer you to solve. So it goes beyond this part of it is maybe less in the puzzle solving. I don't know that there's like a, soft constraint type thing that would apply here um, for most puzzles. But this is really useful in the real world in business, right? Where you're assigning different weights to things that aren't hard and fast. And so just something to think about as you're using Z3, not only in your puzzle solving, but in work and in real life. Okay. Okay, so hopefully you've learned a little bit about the optimizer. I got a little bit of homework for you. Okay, here's what I want you to do. It's a production planning thing. I want you to maximize the profits with resource constraint. So you're a factory worker or a factory manager, and your factory produces two products, chairs and tables. And the chairs sell for $20, but they require an hour of carpentry and 3 hours of painting. Your tables sell for $50, but they require 4 hours of carpentry and 1 hour of painting. So the question you have limited resources per week. You only can do 40 hours of carpentry and 40 hours of painting. So I want you to determine the optimal number of chairs and tables to produce to maximize your revenue, right? So the answer should be you want to make 5 tables or 5 chairs and 2 tables, something like that, right? To give you like the most profit of that thing. If you need some hints, they're down here. If not, avert your eyes. Give it a try. See if you can't solve it. I think it's a cool way to kind of look into. This is, it's a simplified version of real scenarios, right? There are definitely resource constraints in production, and so you have to make decisions. Well, instead of kind of basing it off of gut feelings, you can actually run the numbers, right, and come to a conclusion. What is best? So in this case, we've kind of limited how to solve it for you to practice with your homework, but you can imagine adding many more variables, many more products, and then kind of deciding what to do, right? There's also, there's times where like, oh, we get big orders for chairs, so we need to take that into account. What time of year is it? Maybe we want to prioritize chairs over tables based on the month that we're in. So that's where something like a soft constraint might be interesting for you to look into. So that's a little extra credit. If you want to do a soft constraint in addition to it, I'd love to see it. That's the homework. Okay, that is optimizers. Hopefully you've had a lot of fun learning about optimizers. Again, Z3 is a powerful tool for solving problems, and it's a powerful tool for optimizing those problems, right? So we've shown advent of code style problems that you can solve with an optimizer to get to a solution without knowing like specialized math or anything like that. But we've also, I think, shown real world scenarios, right, that have said, here's how you might solve a real world problem. These are toy problems, but they're not far off from the real world. So hopefully you have an idea now of how you might use the optimizer for Z3, to help solve your problems. Next week, in the next video, I should say, we'll be talking about push pop. So we've shown you a lot of these things, and we have all these different assertions and states of the solver. We can actually like try things. So we can, let's try this and solve it. And if that doesn't work, we back out of that thing and we try another thing. And if that works, maybe we then go a step deeper and try that. And then it doesn't work. And we go up and back and forth. We can go up and back and forth like that to solve problems. And we can do it efficiently using push and pop. So that's what we'll be talking about in the next episode. It's how do we efficiently iterate over problems. So I think that one will be especially useful to me after learning it for like puzzle solving, because I can kind of work out solutions in real time until I come to a solution, until I come to like what I think the right answer is. So Anyway, something very cool for you to like think about is, how do you push pop these states? We'll talk about. And I think that's it. So obviously, I'd love any feedback. And if you have any questions or comments, put them down below. Be happy to help out. If you've got questions on the homework, send them my way. Happy to answer those. If I didn't explain something very well, let me know. I'll definitely, you're probably not the only one. So let me know and I'll explain it, and maybe you'll help yourself out, but other people as well. So otherwise, we'll talk to you next time.